So here you can see the structural analysis of beams using ANSYS mechanical APDL. So in ANSYS, they have defined two types of beams, beam 188, beam 189. So beam 188 is the two-node beam. That is, you can see in the bottom, it will have a nodes only in the I and J, two-node beam. 189 means it will have a three-node, that is in the there is a mid node. So it will have I, J and K. Mid also there is one node. So first one is the linear element and the 189 is the quadratic element. Why this quadratic element is important with the mid node means, for example, here I have shown this is the mesh of 2D and 3D. If it is a linear, it will have the node only at the corners. You can see in the bottom also, only in the corners it has the nodes. If it is a quadratic element, it will have the mid nodes also. Here also you can see there is a lot of mid nodes. So if the number of nodes increases, then we can accurately capture the geometry. Even you can get the accurate results, but it will take more computational time and cost. Here is one example they have shown. In the exact solution first they are given, then they compared with the coarseness of linear element and quadratic element. You can see the linear element, there is much variation between exact and this linear element, but if we take the same coarseness with the quadratic element, it is somehow matches with this exact solution. That's how we can increase the result accuracy also with this quadratic. Then in this ANSYS, finally from the structural analysis of beam, we are going to find bending moment and shear force diagram. Normally in the other ANSYS plane, etc. and all, we will pick the options to get the contour, etc. and all. But in this ANSYS mechanical APDL, they have the element table and they have defined some command outputs for sequence numbers. For example, load is applied on the y direction. Then to get the shear force on the y direction, we have to call this 6 and 19. You have to enter 6 and 19 for this I and J nodes, so that you will get the shear force diagram. And if the load is applied on the y direction, then we can see the moment on the z direction, about which it can rotate. Then you have to choose this moment about the z, mz. Then you have to enter this number 3 and 16, so that you can get the moment diagram on the z. So depends upon the load acting direction, okay, whether it is in y direction, z direction. According to that, you have to choose this my, mz or sf, z, sf, y, etc. You have to choose. And you know the different types of supports. So the first one is the fixed one. That is, it cannot translate, it cannot rotate. It is fixed. Then if it is a roller, you can see along this roller direction, it can translate. Also, it can rotate. So roller means it can translate and rotate. And pinned means it cannot rotate, translate anywhere, but it can rotate. Okay, so fixed means no translation and rotation. Roller means translation and rotation is available. Pinned means no translation, but only it can rotate. So why we are explaining this means, for example, I am going to simulate the simply supported beam. So one side we are taking the pinned support, another side we are taking the roller support. Okay. And this is the shear force bending moment diagram for fixed end simply supported beam. This is the simply supported one. Okay, that's how the shear force diagram and bending moment diagram varies for the fixed end and the simply supported for the point load. And if you vary the load, for example, simply supported beam itself, there is a point load and there is a UDL. This is how shear force and bending moment varies. If it is a fixed end with a point load and UDL, this is how the shear force bending moment varies. In our study, we can also going to check. Maybe we will take this simply supported beam with a point load in the center. That problem we will try now. So already in the last lab manual, they given the same problem. I am taking the same. That is span of 2.2 meters, and there is a load in the center, and they are using the I-beam, and they are using the steel properties. Okay, for this we will simulate now. Mechanical behavior. So only this one you have to round up during that simulation. So now we will go to this mechanical APDL. So two windows open. One is this command window, another one is this main window of this mechanical APDL. And the first step, I am going to define the unit. because we don't know whether it is mm or meter. So the first step, I will define the unit slash unit comma SI. You can give it in small letter or caps something, then enter. Now you can see this command one. Now all the units are in SI units. It is set to the SI. You can see now length is in meter, force is in Newton, mass is in kilogram, time is in second, like that. So whatever you are defining, whatever the bounding condition you are giving, and you should remember these units. According to that, you have to enter the values. We change the unit. Then in the file, I'm going to change at which directory I'm going to save the file and what is the file name. Both I'm going to change. First, we'll change the directory. Maybe I'm going to save it in the desktop. Then the file name may be just simply supported beam. So two things I have changed. Then you can see this main menu. This is similar to the other ANSYS and also last thing I discussed. Like there is a preprocessor, and there is a solution, and there is a post processor. So first we start with this preference. So in this APDL we can do structural, thermal, electromagnetic, etc. So we are going to perform the structural analysis. So start the structural analysis. Then go to the preprocessor where we are going to define the beam, what is the cross section, what is the material, machine, etc. We are going to do this in the preprocessor. So element type, add, select the beam, two types, two node, three node. We for simplicity I will take this two node itself now. So element I have chosen. Then what material I have to define, what is the material model, structural, linear, elastic, isotropic, and defining the steel Newton per meter square, it will be 2 e power 11, and Python this is 0.27. Okay, they have taken meter, okay, so it should be Newton per meter square. So steel property we entered. So element we defined, material we have defined. Now what type of cross section we need? So for the beam, we can choose, can be rectangle or I section, whatever you want. But in the problem, they are given the I section, and they are given 3 centimeter for the W1, W2, around 30 centimeter for the W3, then 2 centimeter thickness. Review if you want. This is the I section they have created. And give OK. So cross section also defined. Okay, element we defined, material we defined, cross section also we defined. Now we can do the modeling. That is complete beam length, etc. and all we can create. So for the modeling, I'm going to create the line. Before that we need the point. So first to create the point, I will use the coordinate point. So I need the 3 points, that is two simply supported ends, center point of the central load. So first point is maybe left side of the point 0, 0, 0. First point is created. And second point where the load will be applied is at 1.1 meter. Then another end will be 2.2 meter. In the problem the given total span is 2.2 meter. So we created all 3 points. Then we can create the line. So first points we created, then line. I'm going to create a straight line, just these 2 points. Then again pick another 2 points, 2 lines are created. So modeling is done. Okay, cross section we defined, line also we have defined. Now we can go for the meshing. Meshing, first I will change the, I'm going to give the number of divisions. For that you have to use this size control. Manually I'm going to enter using this global sizing. I will do just change it 50 divisions on this line. Both section of the line will have 50 divisions. So size control once you done, then you can go for the mesh tool. So mesh, select the line, then OK. Okay, so this is the 2D, 3D view also. At last I will show you how it looks. To yourself better you can see, so that you can apply the load along the y direction. Now with this 2D, the isometric view also it will be like a single line only. To view that cross-sectional view, isometric view and all, you have to go to this plot control, style, size and shape. You have to enable this display of element. Then OK. Now you can see this isometric view. You can see length is along the x direction, flange is in the y direction, and the web is in the z direction. So I am going to apply the load in the z direction only. Okay, so to understand which direction, which axis you want to apply the load, better you can visualize this cross section also. If it is a square cross section, no need to worry, any direction you can apply. If it is a y section or another section, then you should know which direction you are going to apply. So here my loading will be applied on this flange top, okay, along the z direction I'm going to apply. Along the z direction I'm going to apply. Okay, meshing is done. Then we can go for applying the loads. Okay, so after the line creation and the modeling, then meshing is done. Now we can apply the loads. In the load, I'm going to define the loads by applying it. So I'm going to define the load. I'm going to apply the structural load. Okay, apply the structural load. If you expand, you can see displacement and force. So in the displacement, I'm going to apply the displacement on the key points on both the end. Select the key point. First to one end, this will be the pinned end, that is only rotation is allowed. So apply. So I am going to select, that is, there is no translation, only rotation, right? So I am going to select all three translation. I am going to constrain, okay? Is to be constrained, you have to select all the direction, translating motion I have arrested. Then rotation also, I am arresting at x and z. So only by applying this z direction load, okay, applying this z direction vertical top load, it may deflect in the vertical direction, right? That is along the y direction, it may deflect. So, okay. So I am selecting, I am restricting all the translation movements. Then I am restricting the rotation about x and z. It can rotate only about the y-axis. It is perpendicular to the load applying direction. So here I have defined. Then another one displacement at this end. This is like a roller support. That means we are arresting only in the load applying direction. The direction alone simply it is supported. All other direction it can translate, it can rotate anywhere. Okay, like that we are defining it. You can see the symbol. So ready the symbol, you know the coordinate point. So this side I have taken the pinned support, that is it can rotate alone only about the y-axis, along this y-axis. Okay, because we are applying load on the direction, and this side is simply supported on the direction. It can translate, rotate, anything can do. Like that, two sides displacement we have defined. Then load, I am going to apply in the center point. So I am going to apply in the z direction. Okay, the value they are given is 22840. Okay, in the column they are given 22840. So negative downward I am going to apply. So we applied the two deflections and the center load. You can see here. Once everything is finished, you can go for the solution. In the solution, select the solve current LS, that is load step. Okay, solution is done because we have taken just 50 technicians only. Okay, so in the solution, solve current load step. Then you can go for the post processing. The post processing, I have mentioned, we are going to use the element table. We are going to choose the output commands. I and J sequence numbers we have to choose. For that, go to the define table. As the load is applied on the z direction, we have to see the shear force in the z direction now. That is 5 and 18 point we have to call. And it may rotate about the y direction. So we are going to see the bending moment in the 2150 y direction. So we have to call the 2150. Okay. So force is applied on the z direction. So shear force diagram 5 and 18. It may rotate about y direction. So we have to call 2150. Okay. So 215, 5, 18 we have to create that. For that, okay, repeat once again if you want. So node element, define table, add. Here you can enter this the top sequence number, SMISC, as I mentioned, right? Item is SMISC 250. Just I will call it the 2. Actually, in the new version, there are some error. See, it is showing the error. So if you are getting this error, means what you have to do. So that another one window is hidden now. You should have closed first that window, then this error window, then this third window. Sometimes it is it's not coming again. Very weak software. So if you mistakenly selected that, close that error first, then that window is hidden. So to get it back, you can use this price hidden. That window will be coming. So first you have to cancel this, then only you can close this. Otherwise, if you don't know, you have to close this software. Okay, so you can use this raise hidden option to bring that hidden window. So now what we have to do, as I mentioned, you see define table. If you give add number, some number, it's showing the error. I'm trying to apply. Okay, first you have to close this window, then this error, then this one. It will work. Otherwise, that window will be hidden. Okay, now how to resolve this issue means we have to call this command set comma last. Okay, set comma last. So this will retrieve all the results. So just enter. Now we try this define table, add sequence numbers to apply, and it is taken. Okay, so you have to use set comma last. Then 2115 is to for the bending moment diagram. Then 5118 is for the shear force. 5118 is for the shear force. Okay, they have created everything. Now we can go for this plot result. On the plot line element resolution. Here if you call move on 15, you can change the view. You can see the bending moment diagram. Okay, move on 15. There is a bending moment diagram for simply supported beam. As I can capture. Then shear force. Again select the same one. Now you have to call 5118 for shear force. So this is a shear force diagram. Like that, these two you can save it. For saving, you can use this image capture button, capture to file, then OK. And once here you can change example capture to file. Quality you can go for the presentation mode, high quality. Then OK. You have to give some number, PNG, JPEG, and shape force diagram. Whether if you enter in the desktop, the file will be stored here. You can see. And that's how you can save the final file. Okay. So now we have seen that is shear force bending moment diagram on that line. Now you can go for the 3D view. For that you have to go to this nodal solution, DOF, diag displacement vector, apply. You can change the orientation. You can see this how the load is deflected. Okay, the displacement occurred due to the direction force. You can see the displacement. You can see the stressor. Example 1 is the stressors you can see. Okay. Different orientation you can see how it varied from that. So in nodal solution you can see all the displacements that are there. Now, just the orientation I have chosen according to it is coming etc. This is the proper orientation. and along with it we can see the animation also. Same plot control, go to animate and go to this deformed shape. So deform plus undeformed if you take, you can see this how it is deformed. You can see forward, backward, or only forward control. If the load applying in the vertical downward direction, Z direction. So the bar is deformed. You can see other animations also. For example, animate, deformed result. I can see the displacement first. That's how displacement change. Then you can see the stress also. Stress, onward stress. So you can see the animation also. So you can see this line along the line how the bending moment shape of the diagram varies. Then you can see along the 3D view how the displacement surface varies. You can animate also this.